Hey everyone, before we embark on our incredible journey through the cosmos, where are you listening to this video from right now? And what time is it where you are? Maybe you're at home, gazing out your window at the night sky. Or perhaps you're out and about, maybe even driving under the vast, unseen canopy of stars. Wherever you are, take a moment to really feel it. The solid ground beneath your feet, the air on your skin, the sounds around you. And if you can, just for a second, look up. See those pinpricks of light, those distant suns. This you might think is the universe, but what if I told you that the very fabric of that starry tapestry, the colossal structures you glimpse, are not static, eternal monuments, but rather the vibrant living products of an unimaginably ancient birth? What if everything you see out there, from the smallest star to the grandest swirl of a galaxy, is just one breathtaking chapter in a much larger, more bizarre, and infinitely more mind-blowing cosmic saga? Join us on an extraordinary journey as we peel back the layers of time, venturing back to the universe's infancy, to witness the very first moments when the building blocks of galaxies began to stir. We're going to explore the invisible forces, the subtle whispers of gravity, and the spectacular explosions that sculpted the cosmic landscape. We'll challenge everything you thought you knew about the vastness above, and ask the ultimate question: how did our galactic home, and all the billions of others, truly come into being? Imagine for a moment, stepping outside on a clear, moonless night, far away from the glow of city lights. You tilt your head back, and a breathtaking panorama unfolds above you. Thousands upon thousands of stars glitter like scattered diamonds across a velvet cloak. If you squint, or perhaps if you're lucky enough to be in a truly dark sky reserve, you might even glimpse a faint milky band stretching across the celestial sphere, the glorious arm of our own Milky Way galaxy. And if you had a telescope, even a modest one, you could point it at what appears to be an empty patch of darkness and reveal not just a few more stars but fuzzy luminous smudges. Each one of those smudges, almost beyond comprehension, is an island universe, a galaxy, home to hundreds of billions of stars, planets, and countless other celestial bodies, all bound together by the relentless tug of gravity. The sheer scale is dizzying, the beauty profound. But stop and think for a moment. Where did all of this come from? How did these magnificent structures, these cosmic islands, assemble themselves from the raw, unformed material of the early universe? It's a question that has captivated thinkers for centuries. And it leads us on a journey back in time, billions of years, to a universe that bore almost no resemblance to the one we inhabit today. To understand the birth of galaxies, we must first understand the invisible blueprint, the initial conditions that existed long before the first star sparked or the first galaxy coalesced. We need to go back to a time when the universe was, in essence, a blank canvas, yet one with incredibly subtle, almost imperceptible brushstrokes already laid down, destined to become the masterpieces of the cosmos. Our story begins not with stars, but with a whisper, an echo of the universe's earliest moments. Most scientific models agree that our universe began with an event we call the Big Bang. Now, the Big Bang wasn't an explosion in the traditional sense, like a bomb going off in space, with a central point and matter flying outwards into pre-existing nothingness. Instead, it was the rapid expansion of space itself, everywhere, from an incredibly hot, incredibly dense state. Think of it less like an explosion in space, and more like the entire space itself expanding. Imagine a tiny, infinitely hot point that contained all the energy and matter that would ever exist. This point, for reasons still being actively researched, began to expand at an astonishing rate. As it expanded, it cooled. Very, very quickly, within fractions of a second, the fundamental forces of nature that we know today separated, and the elementary particles, quarks, electrons, neutrinos, began to form. For the first few minutes, the universe was a superheated, primordial soup, too hot for even atomic nuclei to fully form, let alone atoms. It was a chaotic, incandescent plasma, a bit like the inside of a star, but much, much hotter and denser, filling all of expanding space. Protons and neutrons, the building blocks of atomic nuclei, were constantly forming and breaking apart. But as the universe continued to expand and cool, a crucial period arrived. nucleosynthesis. For about 3 to 20 minutes after the Big Bang, the temperature and density were just right for protons and neutrons to fuse together, forming the nuclei of the lightest elements, hydrogen and helium, with a tiny trace of lithium. This process was brief, intense, and incredibly efficient. When it was over, the universe had its basic ingredients, about 75% hydrogen nuclei and 25% helium nuclei, by mass, plus a sea of free electrons. There were no heavier elements yet, no carbon, no oxygen, no iron, none of the elements essential for planets or life. Those would come much, much later, forged in the hearts of stars. So at this point, after these first crucial minutes, what did the universe look like? It was still extremely hot, but cooling. It was a dense fog of electrically charged particles, atomic nuclei, protons and helium nuclei, and free electrons. Because these particles were charged, light couldn't travel freely through this cosmic fog. Any photon of light would instantly scatter off an electron, constantly being absorbed and re-emitted, trapped in a cosmic pinball game. The universe was opaque, like peering into the heart of a dense cloud. This period lasted for hundreds of thousands of years. Then came the next pivotal moment, approximately 380,000 years after the Big Bang. By this time, the universe had expanded and cooled sufficiently to about 3,000 degrees Celsius, which is still incredibly hot by Earth standards, but cool enough for a truly transformative event to occur. The free electrons, which had been preventing light from traveling, now had sufficiently low energy that they could combine with the hydrogen and helium nuclei to form the first stable neutral atoms. This process, called recombination, was like the universe taking its first clear breath. With the electrons now bound within atoms, light was suddenly free to travel unimpeded. The universe became transparent, and the light that was released at that moment, the very last photons to scatter off free electrons before the universe became neutral, is still traveling across the cosmos today. We detect it as the cosmic microwave background, or CMB. The cosmic microwave background is arguably the most profound piece of evidence supporting the Big Bang model, and it is the key to understanding the invisible blueprint of galaxies. Imagine taking a snapshot of the universe when it was just 380,000 years old, when it was still incredibly young and relatively uniform. That's what the CMB is. It's an almost perfectly uniform glow of microwave radiation coming from every direction in space. When first detected serendipitously in the 1960s by Arno Penzias and Robert Wilson, it was initially mistaken for pigeon droppings or some other interference, but it was quickly recognized as the predicted afterglow of the Big Bang, a cosmic echo of the universe's fiery birth. Now, while the CMB is remarkably uniform, it's not perfectly uniform. This is where the blueprint for galaxies truly begins to reveal itself. Thanks to missions like COBE, WMAP, and Planck, we've been able to map the CMB with incredible precision. What these maps reveal are tiny, almost imperceptible temperature fluctuations, differences of merely 1 part in 100,000. Think of it like this. If you could view the entire universe as a perfectly smooth, warm, cosmic ocean, these fluctuations would be like ripples on its surface, so subtle you might not even notice them unless you looked very, very closely. Some areas are infinitesimally warmer, others infinitesimally cooler. These tiny temperature variations are immensely significant because they correspond to equally tiny variations in the density of matter in the early universe. The slightly cooler spots are where matter was ever so slightly denser, and the slightly warmer spots are where it was slightly less dense. These overdense regions, though incredibly small in magnitude, were the seeds of all future structure in the universe. They were the very first gravitational whispers, the subtle beginnings of everything we see today. Without these initial inhomogeneities, these tiny ripples, gravity would have had nothing to work with. A perfectly smooth universe would have expanded forever, remaining eternally featureless, a dilute cosmic fog with no stars, no planets, no galaxies, and certainly no life. The existence of these subtle density fluctuations in the CMB is a direct testament to the fundamental starting conditions that allowed galaxies to form. But these seeds alone weren't enough. There was another crucial invisible player, far more abundant than the ordinary matter we've discussed: dark matter. For decades, astronomers observed that galaxies were spinning too fast, and galaxy clusters were too gravitationally bound for the amount of visible matter they contained. Something unseen, something extra, had to be providing the additional gravitational pull. This mysterious substance is what we call dark matter. We can't see it directly. It doesn't emit, absorb, or reflect light. It doesn't interact with the electromagnetic force, which is why it's dark. But it does interact gravitationally. It has mass, and it exerts a gravitational pull. And here's the kicker. Dark matter is estimated to make up about 27% of the universe's total mass energy content, while ordinary matter, the stuff stars, planets, and we are made of, accounts for only about 5%. The rest, about 68%, is an even more mysterious force called dark energy, which is responsible for the accelerating expansion of the universe. But that's a story for another time. For the purpose of galaxy formation, the key takeaway is this: dark matter is roughly 5 times more abundant than ordinary matter. This dominance of dark matter is absolutely critical to the formation of galaxies. Why? Because ordinary matter, at the time of the CMB and shortly thereafter, was still too hot and too energetic to collapse under its own gravity. It was pushing back against gravity with its own internal pressure. Dark matter, however, doesn't feel this pressure. It doesn't interact with light, and it doesn't interact with itself in the same way ordinary matter does. This means that when the universe was still hot and dense, the dark matter was already beginning to gather in those slightly overdense regions, pulling itself together under its own gravity, unhindered by the thermal pressure that affected ordinary matter. Think of dark matter as the invisible scaffolding, the unseen skeleton of the universe, even before ordinary matter could begin to cool and settle. Dark matter was already starting to clump together in those regions indicated by the CMB ripples. It was forming invisible gravitational wells, like subtle dips in the cosmic landscape. These dips, these pockets of slightly higher dark matter density, were the foundational structures, the cosmic cocoons, within which ordinary matter would eventually collect and condense. Without dark matter acting as this early gravitational anchor, ordinary matter would have had a much harder time forming structures. It would have remained far more diffuse and spread out, unable to overcome the immense pressure of its own heat and the rapid expansion of the universe. So when we look back at the universe before galaxies, what do we truly see? We see a universe that has just cooled enough for light to travel freely, revealing the cosmic microwave background. We see an almost perfectly uniform canvas, but one with the most subtle yet profoundly important ripples, minute variations in density that are the first faint gravitational whispers. And crucially, we see a universe dominated by an invisible, gravitationally active substance called dark matter, already beginning to respond to those whispers, slowly but surely forming the foundational structures, the invisible gravitational wells that would ultimately serve as the nurseries for the first stars and eventually the grand galaxies we marvel at today. This period, after the CMB formed but before the first stars ignited, is often referred to as the cosmic dark ages, a time when the universe was mostly neutral hydrogen and helium gas, unlit by stars, quietly evolving under the slow, patient, and relentless pull of gravity, laying down the invisible blueprint for all the magnificent structures that were yet to be born. The stage was set, the ingredients were in place, and the invisible scaffolding was beginning to take shape, patiently awaiting the dramatic events that would follow. Chapter 2. The cosmic web begins to weave, first filaments and halo. In our last chapter, we set the stage for the birth of galaxies, peering back to a universe that was profoundly different from the star-studded cosmos we know. We explored the immediate aftermath of the Big Bang, the formation of the first light elements, and the pivotal moment when the universe became transparent, releasing the echo we now detect as the cosmic microwave background. Crucially, we learned that embedded within this ancient light were minuscule temperature fluctuations, cosmic ripples that corresponded to tiny, almost imperceptible overdensities in the distribution of matter. And perhaps most importantly, we introduced the invisible, dominant force of dark matter, a substance that makes up the vast majority of the universe's mass and interacts only through gravity. We painted a picture of a universe entering its dark ages, a vast expanse of neutral hydrogen and helium gas, unlit by stars, but with an unseen blueprint of gravitational potential already laid down. Now we move from the blueprint to the slow, inexorable construction. Imagine a truly immense cosmic expanse, cold and dark, stretching billions of light years in every direction. Within this expanse, the tiny overdensities of matter, particularly dark matter, are like microscopic hills and valleys on an otherwise flat plane. But these aren't static hills. They are gravitational attractors, subtle at first, but relentless. This is where gravity, the most patient and persistent sculptor in the universe, truly begins its work. Consider gravity's unique nature. It's always attractive, never repulsive. It always pulls things together. And its strength depends on mass and distance. In the very early universe, with matter distributed almost uniformly, gravity's pull was relatively weak and symmetrical. But those tiny overdensities, those almost imperceptible regions where matter was even a fraction of a percent more concentrated, represented a crucial imbalance. In these slightly denser spots, gravity was ever so slightly stronger than in the surrounding regions. This minute difference over vast stretches of time would prove to be monumental. Picture a vast, unmoving ocean. Now imagine a tiny ripple, just a few millimeters high. It might seem insignificant, but that ripple is slightly higher than the surrounding water. If there were a mechanism for water to slowly accumulate, that tiny ripple would attract more water, growing slightly taller. As it grows, its gravitational pull subtly increases, drawing in even more water. This is a simplified analogy for what happened with dark matter. The overdense regions, however slight, began to attract more dark matter from their immediate surroundings. As they pulled in more dark matter, they became even denser, and their gravitational pull grew stronger still. This created a positive feedback loop. Denser regions attract more matter, becoming even denser, accelerating the pull. This process is often called gravitational instability or runaway collapse. But this was not a swift process. We are talking about cosmic timescales. For hundreds of millions of years during the cosmic dark ages, while the universe continued its inexorable expansion, dark matter was patiently, slowly, almost imperceptibly clumping together. This initial period of gravitational growth was dominated by dark matter precisely because it didn't interact with light or with itself in the complex ways ordinary matter does. Ordinary matter, still relatively hot, was subject to internal pressure that resisted gravitational collapse. Dark matter, however, was cold in the sense that it didn't have significant random motion or thermal pressure pushing back. It just followed gravity's pull. As dark matter accumulated in these overdense regions, it began to form the first significant structures in the universe, dark matter halos. Imagine these not as solid, well-defined objects, but as vast, diffuse, invisible clouds of dark matter, extending for hundreds of thousands, even millions of light years across. They were not perfectly spherical, but often lumpy and irregular, reflecting the chaotic nature of gravitational collapse. These halos were the deepest gravitational wells in the early universe, the regions where gravity had concentrated the most mass. They were the cosmic equivalent of invisible gravitational traps, patiently waiting to collect the raw materials that would one day form stars and galaxies. These dark matter halos weren't isolated islands. The early universe, though largely uniform, had these tiny ripples spread across it. As gravity worked its magic, the matter didn't just clump into spheres. Instead, it began to flow from regions of lower density towards regions of higher density. Think of it like water on a vast, almost flat landscape. Water will always flow downhill, seeking the lowest point. Similarly, matter in the early universe flowed from the valleys of low density towards the hills of high density. But this wasn't a simple, direct flow. Over time, this gravitational flow started to carve out a magnificent, interconnected structure throughout the entire observable universe, the cosmic web. Imagine a colossal three-dimensional spider web stretched across billions of light years. This web is not made of silk, but of dark matter. The thickest strands of this web are called filaments, long, rope-like structures where dark matter has accumulated. Where these filaments intersect, where several strands meet, you find the densest knots, the largest concentrations of dark matter. These are the sites of the most massive dark matter halos. These are the sites of the most massive dark matter halos. In between these filaments and knots are vast, flatter regions called sheets or walls, where dark matter has accumulated to a lesser extent, forming a membrane-like structure connecting the filaments. And in between these sheets and filaments are enormous, almost entirely empty regions called voids. These voids are not truly empty. They still contain some diffuse matter, but it's far less dense than average, as gravity has steadily pulled matter out of them and into the surrounding filaments and halos. The cosmic web, therefore, is a beautiful, intricate cosmic architecture, vast, empty voids interspersed with tenuous sheets which connect to dense filaments, culminating in the most massive dark matter halos at their intersections. It looks remarkably similar to the neural networks of a brain or the intricate structure of a sponge. The formation of this cosmic web is a fundamental prediction of our cosmological models, and it has been dramatically confirmed by astronomical observations. When astronomers map the distribution of galaxies on the largest scales, they don't find them randomly scattered like confetti. Instead, they see precisely this web-like structure, galaxies clustered in filaments and walls with vast empty regions in between. This observational evidence serves as a powerful confirmation that the invisible dark matter provided the initial scaffolding for the visible universe we inhabit. Without the cosmic web of dark matter, the visible galaxies would not exist in their observed patterns. So, while the cosmic dark ages were truly dark, without the light of stars, they were a period of intense, unseen gravitational activity. The universe was not static, it was dynamic, with dark matter slowly but surely congealing into these vast, interconnected structures. The dark matter halos were growing, pulling in more and more dark matter, becoming deeper and deeper gravitational wells. But what about the ordinary matter, the hydrogen and helium gas that would eventually form stars and planets? While dark matter was building its invisible scaffolding, the ordinary gas was still largely diffuse and hot. Remember, after the universe became transparent, the gas was still at a temperature of about 3000 degrees Celsius. As it expanded, it cooled further, but not enough to easily collapse on its own. It was still hot, and its own internal thermal pressure strongly resisted gravitational collapse. Imagine trying to compress a hot gas. It pushes back. This is fundamentally different from dark matter, which doesn't experience this kind of pressure. However, as the dark matter halos grew and the cosmic web solidified, their immense gravitational pull began to exert a significant influence on this diffuse ordinary gas. The gas, feeling the stronger gravitational attraction from the growing dark matter concentrations, started to slowly fall into these gravitational wells. It was like a slow cosmic rain, with the gas particles gradually drifting from the less dense voids and sheets towards the more massive filaments and halos. But as the gas fell deeper into these gravitational wells, it encountered a significant challenge. As any gas falls into a gravitational potential, it gains kinetic energy and heats up. Think of a meteor falling through Earth's atmosphere. It gets incredibly hot due to friction. In a similar way, as vast clouds of hydrogen and helium gas fell into the gravitational embrace of the dark matter halos, they compressed and heated up. This heating process, in turn, increased the gas's internal pressure, making it even harder for gravity to compress it further. It was a tug of war, gravity pulling the gas in, but the gas's own heat and pressure pushing back. For ordinary matter to collapse sufficiently to form stars, it needs to get rid of this excess heat. It needs to cool down. If the gas remains hot and pressurized, it will simply bounce around within the halo, unable to condense into dense enough pockets to ignite nuclear fusion. This inability of the ordinary gas to efficiently cool and condense was a major bottleneck during the cosmic dark ages. The dark matter was doing its job, providing the gravitational scaffolding, but the ordinary gas was lagging behind, still too energetic. The timescale for this process is staggering. From the moment the universe became transparent and the CMB formed, It took hundreds of millions of years for these dark matter halos to grow large enough and deep enough to start significantly collecting ordinary gas. This was a period of immense cosmic patience where unseen forces slowly shaped the future of the universe. The universe was expanding, yes, but within these expanding boundaries, gravity was diligently working to counteract that expansion in localized regions, pulling matter together. So by the end of this epoch, the cosmic dark ages were drawing to a close. We had a universe permeated by an intricate, interconnected cosmic web of dark matter. At the nodes and along the filaments of this web, the most massive dark matter halos had formed, vast, invisible gravitational cocoons. Within these cocoons, ordinary hydrogen and helium gas was slowly but surely accumulating. It was compressed, heated, and beginning to settle. But it wasn't yet dense enough or cool enough to spark the momentous event that would finally bring light to the universe. The dark matter halos were built. The gas was gathered, but the switch hadn't been flipped. The nurseries were constructed, but the first cosmic babies, the first stars, had not yet been born. This grand, slow dance of gravity and dark matter was setting the stage for the true dawn of light, for the beginning of stellar ignition that would fundamentally transform the universe from a dark, featureless expanse into a vibrant, luminous tapestry of galaxies. This transition, from invisible scaffold to incandescent stars, is the thrilling next chapter in our cosmic story. Chapter 3. The first stars ignite, lighting up the dark ages. In our journey so far, we have delved into the universe's infancy, witnessing the immediate aftermath of the Big Bang, the formation of the simplest elements, and the profound moment when light was finally released, giving us the cosmic microwave background. We then explored the long, patient work of gravity, how it acted upon tiny density fluctuations in the early universe, allowing the mysterious dark matter to slowly coalesce and form the invisible scaffolding of the cosmic web, a vast, intricate network of filaments, sheets, and enormous voids, with massive dark matter halos forming at its densest knots. By the end of our last chapter, we left the universe in its dark ages, a time when ordinary hydrogen and helium gas was slowly, almost reluctantly, falling into the deep gravitational wells of these dark matter halos. The nurseries were built, the raw material was gathered, but the spark, the fundamental light that would ignite the cosmos, was yet to appear. This chapter will illuminate that momentous ignition, the birth of the universe's very first stars, and the dramatic, irreversible transformations they unleashed upon the young cosmos. The critical hurdle for the ordinary gas accumulating within those dark matter halos was cooling. Imagine trying to make a cloud of steam condense into a puddle of water. It won't happen if the steam is too hot and energetic. Similarly, the hydrogen and helium gas falling into the dark matter halos was still quite warm, heating up even further as it fell deeper into the gravitational potential. This meant its internal pressure was significant, pushing outwards and resisting the inward pull of gravity. For a star to form, the gas needs to become incredibly dense, much denser than it was in these diffuse clouds. This densification requires the gas to shed its thermal energy, to cool down efficiently, allowing gravity to overcome pressure and squeeze the matter into an ever smaller volume. In the universe today, gas clouds cool very effectively by radiating away energy, often through the emission of light by heavier elements like carbon and oxygen. These metals, as astronomers broadly call any element heavier than helium, act as cosmic refrigerants, allowing gas clouds to radiate energy efficiently and cool down quickly. But in the early universe during the Dark Ages, there were no metals. The gas was almost entirely pristine hydrogen and helium, the direct products of the Big Bang. This made cooling a far more challenging and less efficient process. The primary way this primordial gas could cool was by the emission of light from excited hydrogen molecules. It was a slow, difficult, and laborious process, like trying to cool a large room with only a tiny, inefficient fan. Despite these challenges, in the very densest hearts of the largest dark matter halos, where the gravitational pull was strongest and the concentration of gas was highest, the slow process of cooling finally began to win the battle against thermal pressure. As the gas continued to collapse, its density increased. This further compression led to even more frequent collisions between particles, and while these collisions generated heat, the overall structure was slowly able to radiate away some of that energy. Eventually, within these highly concentrated pockets, the gas became dense enough to become unstable to further collapse. Think of it as a crucial threshold being crossed, where the inward pressure of gravity finally overwhelms the outward push of thermal energy. These collapsing clumps of pristine hydrogen and helium were the embryonic forms of the first stars, known as protostars. They weren't yet shining, but they were furiously contracting under their own immense gravity, their cores growing hotter and denser with each passing millennium. This gravitational contraction was a continuous process, drawing in more and more surrounding gas. The turbulence within these collapsing clouds was enormous, with gas spiraling and colliding, creating a chaotic environment. But at the very center, a core of incredible density was forming. What were these first stars like? Because they formed from gas that contained absolutely no heavier elements. No carbon, no oxygen, no nitrogen, no silicon, no iron. They were fundamentally different from the stars we see today, like our Sun. Stars today are called population I or population II stars, depending on their metallicity or the abundance of heavy elements within them. The first stars, however, are hypothesized to have been population III stars, a purely theoretical population that has never been directly observed, but whose existence is a cornerstone of our understanding of cosmic evolution. Without metals to act as coolants, the gas clouds needed to accumulate far more mass and reach much higher temperatures and densities before they could finally ignite nuclear fusion. This meant that the first stars were overwhelmingly massive. Theoretical models suggest they were typically dozens, even hundreds of times more massive than our Sun, perhaps even up to 1,000 solar masses in some cases. Imagine a single star weighing as much as 1,000 suns. This is a dramatic departure from the stars we observe in our galaxy today, where stars ranging from a fraction of the Sun's mass to about 50 or 60 times the Sun's mass are common. But stars much larger than that are exceedingly rare. Because of their immense mass, these population III stars would have been incredibly hot and incredibly luminous. They would have burned through their nuclear fuel at an astonishing rate, radiating vast amounts of energy across the electromagnetic spectrum, especially in the powerful, high-energy ultraviolet range. And precisely because they burned so fiercely, their lives were spectacularly short. While our Sun will live for about 10 billion years, and smaller stars can live for trillions of years, these first massive stars would have existed for only a few million years, a mere cosmic blink of an eye. Their lives were brief, but their impact would be nothing short of revolutionary. The moment of ignition, when nuclear fusion finally began in the core of one of these protostars, was a watershed event in cosmic history. At immense temperatures and pressures, hydrogen nuclei, the simplest of atoms, were forced together to fuse, creating helium nuclei and releasing an unimaginable burst of energy in the process. This was the moment the cosmic dark ages truly ended. For the first time since the universe became transparent, hundreds of millions of years earlier, pockets of incandescent light flared into existence. The universe, which had been a mostly dark, neutral expanse, was now pierced by the brilliant, searing light of its very first stars. The profound impact of these first stars extended far beyond their mere existence as points of light. Their immense radiation and explosive deaths fundamentally transformed the universe in two crucial ways: cosmic reionization and chemical enrichment. Let's first consider cosmic reionization. Recall that after the universe became transparent at 380,000 years, the vast majority of hydrogen atoms were neutral. This means their electrons were bound to their protons. While light could now travel, if it traveled too far, it would eventually encounter a neutral hydrogen atom. Neutral hydrogen is very efficient at absorbing high-energy ultraviolet light. This meant that even though the universe was transparent to visible light, like the CMB, it was still largely opaque to the very energetic ultraviolet radiation that would come from the first stars. It was like trying to see through a dense fog, but a fog that specifically absorbed high-energy light. The population III stars, however, were so hot and so luminous that they emitted prodigious amounts of this very high-energy ultraviolet radiation. This UV light was powerful enough to strip electrons away from the neutral hydrogen atoms in the surrounding gas, leaving them ionized, meaning the protons and electrons were now separate again, as they had been in the very early universe. This process is called ionization. As the first stars ignited, they began to carve out vast bubbles of ionized hydrogen around themselves. These bubbles grew larger and larger as more and more UV photons streamed out from the stars, gradually eating away at the surrounding neutral hydrogen fog. Imagine a dense, omnipresent fog. Now imagine powerful spotlights turning on within that fog. Each spotlight creates a clear, illuminated sphere around itself, where the fog has been dispersed. As more spotlights turn on, these clear spheres expand, eventually merging. This is an analogy for reionization, as more and more population 3 stars formed within their respective dark matter halos, and as their powerful UV radiation propagated outwards, these individual bubbles of ionized gas grew and merged. Over hundreds of millions of years, from roughly 150 million years after the Big Bang until about 1 billion years after the Big Bang, the universe transitioned from being largely neutral and opaque to UV light, to being almost entirely ionized and transparent. This reionization was a critical step in the evolution of the cosmos. Without it, light from distant galaxies would have been absorbed, and we wouldn't be able to observe the far reaches of the universe as we do today. The universe would have remained largely shrouded, a cosmic secret. The first stars were the agents that pulled back that veil. The second profound impact of the first stars was chemical enrichment. Remember, the universe after the Big Bang was made almost exclusively of hydrogen and helium. All the heavier elements, carbon, oxygen, which make up our bodies and Earth, silicon for rocks, iron for blood and planetary cores, and countless others, did not exist. They had to be forged, and the first cosmic furnaces capable of forging these elements were the very first stars. During their short, intense lives, massive stars fuse lighter elements into heavier ones in their cores. They start with hydrogen, fusing it into helium. Then, as they run out of hydrogen in their cores, they move on to fusing helium into carbon and oxygen, and so on, building up layers of progressively heavier elements in their interiors, much like an onion. This process, called stellar nucleosynthesis, creates all the elements up to iron, but the truly dramatic moment comes at the end of their lives. When a massive star exhausts its nuclear fuel, its core can no longer withstand the immense inward pull of gravity. It collapses catastrophically, triggering a rebound explosion of unimaginable power known as a supernova. These are the most luminous explosions in the universe, briefly outshining entire galaxies. In the cataclysmic temperatures and pressures of a supernova, elements heavier than iron are forged through rapid neutron capture, and critically, the explosion itself blasts all these newly synthesized elements, the carbon, the oxygen, the silicon, the iron, and even the gold and uranium, out into the surrounding interstellar medium. Imagine the universe as a pristine, empty canvas. The Big Bang painted it with pure hydrogen and helium. Then, the first stars appear, shining brilliantly for a short time, and then explode, splattering the canvas with the first flecks of color, the first heavy elements. These supernovae represented the universe's first element factories. They were the initial distributors of the chemical building blocks that would eventually make planets, oceans, and life possible. The gas in the early universe, once purely hydrogen and helium, now became polluted with these new, heavier elements, which astronomers refer to as metals. This metallicity is crucial because, as we discussed, these heavier elements are far more efficient at cooling gas clouds. This would have profound implications for future generations of stars. This process of feedback from the first stars was a complex dance. On one hand, their radiation reionized the universe, clearing the way for light. Their supernovae enriched the cosmic gas with vital new elements. On the other hand, the intense radiation and powerful supernova blasts could also be destructive. They could heat and blow away the surrounding gas in the halos, making it harder for new stars to form in their immediate vicinity. It was a push and pull, a constant interplay between creation and disruption. The legacy of these short-lived, elusive population 13 stars is immense, though we have yet to directly observe one. Our understanding of cosmic evolution demands their existence. They were the trailblazers, the pioneers, fundamentally altering the conditions of the universe. They transitioned the cosmos from a dark, featureless expanse to one that was transparent and chemically enriched. They provided the essential ingredients and conditions for the next, even more complex stage of cosmic evolution, the assembly of galaxies, the true islands of stars that define our universe today. The universe was no longer just a collection of gas and dark matter. It was now a dynamic, chemically evolving system, ready for the grand assembly of its most magnificent structures. The stage was now truly set, not just for isolated stars, but for the vast swirling collections of stars that would eventually become the familiar galaxies, ushering in the true dawn of galactic life. The next chapter will explore how these chemically enriched, transparent regions began to coalesce into the magnificent structures we call galaxies. Chapter 4. Galactic Toddlers, Building Blocks and Early Mergers. Our journey through cosmic history has taken us from the universe's earliest moments, through the Big Bang and the release of the cosmic microwave background, and into the long, dark epoch where gravity patiently wove the invisible cosmic web of dark matter. In our last chapter, we witnessed a truly pivotal event, the dramatic ignition of the first stars, the incredibly massive and short-lived population third stars, which ended the cosmic dark ages by bathing the universe in light. More importantly, these stellar pioneers, through their intense radiation, began the process of cosmic reionization, transforming the opaque neutral hydrogen fog into a transparent, ionized plasma, and through their spectacular supernova explosions, they achieved something equally profound. They forged and scattered the very first heavy elements, the carbon, oxygen, nitrogen, and iron, into the universe's once pristine canvas of hydrogen and helium. These metals, as astronomers broadly define them, were the game changers, setting the stage for the next crucial phase of cosmic evolution. Now we move beyond individual stars to the formation of the first gravitationally bound collections of stars, the galactic toddlers, the proto-galaxies, the building blocks that would eventually assemble into the magnificent island universes we observe today. The universe, no longer uniformly pristine, now harbored regions enriched with these newly forged metals. This seemingly subtle change had enormous implications for how new stars would form, and consequently, how galaxies would begin to coalesce. Think back to the challenge of cooling that faced the gas forming the very first stars. With only hydrogen and helium available, cooling was inefficient, requiring enormous amounts of gas to collapse before reaching the densities and temperatures necessary for ignition. This bias towards massive initial collapses led to the formation of those behemoth population the third stars. But now, with the advent of even trace amounts of carbon, oxygen, and other heavier elements, the cooling problem was significantly alleviated. These metals act as far more efficient cosmic refrigerants. They have more complex electron configurations and atomic structures that allow them to absorb energy from the gas and re-emit it more effectively as infrared light, carrying away heat and allowing the gas to cool much faster. This enhanced cooling efficiency was a game changer. It meant that smaller clumps of gas within the dark matter halos could now cool, condense, and collapse under their own gravity to form stars. No longer did you need only the most massive, hottest regions. This allowed for the formation of subsequent generations of stars, the population 2 stars. Our Sun is population 1, very metal-rich, but Pop 2 are older and less metal-rich. They were generally less massive and significantly longer lived than their population 3 predecessors. These stars, more akin to those we see today, could sustain star formation for much longer periods, providing a more stable and continuous source of light and energy within their nascent systems. Within the growing dark matter halos, especially those forming at the intersections of the cosmic web filaments, the chemically enriched gas continued to flow inwards. As this gas cooled more efficiently, it accumulated at the very centers of these dark matter concentrations, becoming dense enough to foster the birth of not just 1 or 2 massive stars, but entire populations of smaller, longer-lived stars. These nascent systems, gravitationally bound collections of hundreds of thousands or even millions of stars, along with residual gas, dark matter, and the dust formed from the supernovae of earlier stars, are what we refer to as proto-galaxies or mini-galaxies. These weren't the grand, majestic spirals or smooth, colossal ellipticals we picture when we think of galaxies today. Instead, imagine them as chaotic, irregular, clumpy aggregations. They were more akin to the dwarf galaxies we observe in the universe today, or perhaps even smaller, resembling turbulent star-forming regions rather than organized structures. Their shapes were dictated by the messy, violent process of their formation, with gas still falling in from all directions and the young stars lighting up in bursts. A cornerstone of our modern understanding of galaxy formation is the concept of hierarchical formation, often described as a bottom-up process. This means that galaxies didn't form as massive, fully fledged entities in one swift collapse. Instead, they grew by gradually assembling smaller pieces, like building a colossal structure with Lego bricks. The smallest dark matter halos formed first, providing the gravitational cradles for the first stars and proto-galaxies. These smaller systems then began to merge and accrete, slowly building up larger and larger structures over cosmic time. Consider the analogy of a snowball rolling downhill. It starts small, but as it rolls, it picks up more and more snow, growing steadily larger. Galaxy formation works similarly. The smallest clumps of dark matter and gas formed first. These then pulled together, merged and grew, eventually forming larger dark matter halos, which in turn attracted more gas and swallowed smaller galactic fragments. This contrasts sharply with earlier top-down theories, which posited that vast, massive clouds of gas collapsed to form entire galaxies all at once. Modern cosmological simulations, which incorporate dark matter, dark energy, and the physics of gas, overwhelmingly support the bottom-up, hierarchical model. And this hierarchical growth was profoundly driven by mergers. The early universe was a far denser, more compact place than it is today. All the matter and structures were packed more closely together. This meant that the proto-galaxies, along with their encompassing dark matter halos, were constantly encountering each other. Collisions and mergers between these nascent galactic systems were not rare events. They were the norm, the primary engine of galactic growth and evolution during the universe's formative years. What exactly happens during a merger of these galactic toddlers? It's important to understand that it's not a direct collision of stars, like billiard balls smashing into each other. The distances between individual stars, even within a galaxy, are immense. If our sun were a grain of sand, the nearest star would be miles away. So when two galaxies merge, the stars within them generally pass through each other unscathed, their individual motions largely undisturbed by direct impact. However, the gravitational interaction between the merging systems is immense and transformative. As two proto-galaxies approach each other, their colossal dark matter halos and the gas and stars within them begin to exert powerful tidal forces on each other. Imagine two enormous gravitational whirlpools tugging and pulling, stretching and deforming each other. These tidal forces can disrupt the delicate balance of gas clouds, trigger waves of star formation, and completely alter the orbits of billions of stars. It's a chaotic, violent, yet ultimately creative dance. The gas dynamics during a merger are particularly crucial. Unlike stars, which are largely collisionless, gas clouds do collide. When the vast gas clouds from two merging proto-galaxies meet, they crash into each other with tremendous force. These collisions generate powerful shock waves that compress the gas to incredibly high densities and temperatures. This compression often leads to spectacular, rapid bursts of star formation, known as starbursts. For a brief period, the merged system can shine with the luminosity of hundreds of billions of suns as new stars ignite en masse. This starburst activity consumes vast amounts of gas very quickly, turning it into stars or expelling it from the galaxy entirely due to stellar winds and supernova explosions. The stellar orbits within the merging systems are also dramatically affected. While individual stars don't collide, their paths around the galactic center are drastically altered by the changing gravitational field. Imagine a cosmic mosh pit. the stars are thrown into new randomized orbits, often losing any organized disk-like structure they might have been trying to form. Repeated major mergers of proto-galaxies and smaller fragments would tend to homogenize the stellar distribution, stirring up the component stars and gas into a more spheroidal, less organized shape. These frequent, energetic mergers were the primary architects of the morphological evolution of early galaxies. If a proto-galaxy managed to grow largely through the steady accretion of fresh, cool gas from the cosmic web filaments, and if it avoided major disruptive mergers, that infalling gas, carrying angular momentum, a kind of cosmic spin, would tend to settle into a rotating disk, slowly giving rise to what would eventually become a spiral galaxy. However, in the chaotic early universe, such undisturbed growth was often rare. The more common scenario involved repeated mergers of these smaller, irregular systems. These mergers, especially those of roughly equal-sized proto-galaxies, were particularly effective at destroying any nascent disks and randomizing stellar orbits, leading to the formation of more diffuse, often elliptical-shaped systems. As these mergers continued, the dark matter halos at the nodes of the cosmic web grew increasingly massive. They became the gravitational behemoths, attracting not just gas, but also entire smaller proto-galaxies. The most massive galaxy within such a large dark matter halo would establish itself as the central galaxy, growing by repeatedly cannibalizing smaller satellite galaxies that fell into its gravitational sphere of influence. This process continues even today, with our own Milky Way currently in the process of consuming several smaller dwarf galaxies. The central galaxy grew not just by turning its internal gas into stars, but also by adding entire preformed stellar systems to its mass. Beyond mergers, the continuous infall of fresh gas from the cosmic web filaments also played a crucial role. These filaments acted like cosmic arteries, funneling cool gas from the vast voids and sheets towards the dense nodes where galaxies were forming. This fresh supply of gas provided the fuel for ongoing star formation within the growing proto-galaxies, ensuring that even after a merger-induced starburst subsided, new stars could continue to be born, adding to the galaxy's stellar mass. The interplay between chaotic merger events and steady, calmer gas accretion was a dynamic dance that sculpted the early universe. It is crucial to remember the vast timescales involved in this cosmic ballet. From the first stars igniting around 150-200 million years after the Big Bang, the universe spent the next 1 to 2 billion years in this phase of intense proto-galactic growth and assembly. This period, sometimes referred to as the epoch of galaxy assembly, was characterized by rapid, often violent evolution. The universe was far more active and turbulent than it is today, with galaxies colliding and merging at a furious pace, constantly reshaping themselves and growing in mass. By the time the universe was 2 or 3 billion years old, these galactic toddlers had grown significantly. The smallest ones might have remained dwarf galaxies, relatively undisturbed, but the larger ones, having undergone multiple mergers and continuous gas accretion, had amassed billions of stars and were beginning to take on more recognizable forms. Some were still irregular, clumpy, and highly active, but others were starting to settle into early versions of the grand spirals, or the smooth, quiescent ellipticals we observe in the mature universe. The foundations for the diverse array of galaxies we see today were firmly laid during this turbulent, merger-driven epoch. The next chapter will delve into how these early forms matured and diversified into the magnificent, distinct galactic types that populate our cosmic neighborhood. Chapter 5: The Grand Designs, Spirals, Ellipticals, and Supermassive Black Holes. Our cosmic narrative has carried us from the featureless infancy of the universe, through the invisible scaffolding of dark matter, and into the turbulent epoch where the first stars blazed and then died, enriching the cosmos with the crucial building blocks of life. We then plunged into the era of galactic toddlers, witnessing the chaotic and frequent mergers of proto-galaxies, those irregular, clumpy collections of young stars and chemically enriched gas, all driven by the relentless process of hierarchical, bottom-up growth. These early galactic systems, while growing steadily larger, were still far from the elegant grand designs that populate our modern universe. Now we arrive at the pivotal stage where these amorphous building blocks mature and diverge, sculpted by their unique histories into the two dominant galactic morphologies, the magnificent spirals and the serene ellipticals. We will also uncover a powerful, often enigmatic force that resides at the heart of nearly every large galaxy, the supermassive black hole, whose influence is deeply intertwined with the very life and death of its host galaxy. By the time the universe was 2 to 3 billion years old, the frantic pace of early mergers had begun to subside somewhat, especially for galaxies forming in less dense regions. The gas had continued to cool, now more efficiently thanks to the presence of heavier elements forged by the first stars. This cooling allowed vast quantities of gas to settle deeper into the gravitational wells of their dark matter halos. The trajectory of a galaxy's evolution, whether it would become a majestic spiral or a smooth elliptical, was determined by a delicate interplay of its environment, its merger history, and the physics of the gas within its boundaries. This was the era of the grand designs, where the universe began to sketch the diverse tapestry of galactic forms we see today. Let us first explore the genesis of spiral galaxies, like our own Milky Way. These galaxies are characterized by their distinct flattened disks, often adorned with graceful luminous spiral arms and a central bulge of stars. Their formation hinges on a crucial factor, the steady, continuous inflow of cool gas from the surrounding cosmic web, coupled with the gas retaining its angular momentum or its intrinsic spin. Imagine a vast cloud of gas and dark matter slowly collapsing. As this cloud contracts under gravity, any initial slight rotation within it becomes amplified, much like an ice skater spinning faster as she pulls her arms in. This principle, known as conservation of angular momentum, is fundamental to disk formation. As the gas falls into the gravitational potential of the dark matter halo, it doesn't simply plummet straight to the center. Because gas particles can collide with each other, they lose energy. Crucially, while they lose energy, they conserve their angular momentum. This combination of energy loss and angular momentum conservation forces the gas to flatten out into a rotating disk, much like how a spinning ball of pizza dough flattens into a large thin crust. The gas continues to cool within this disk, becoming dense enough to form new stars. These new stars are born within the disk, inheriting its rotational motion, contributing to its flattened shape. The spiral arms themselves are not rigid structures that rotate like spokes on a wheel. Instead, they are thought to be density waves, regions where gas and dust are temporarily compressed, triggering bursts of star formation. As the gas flows through these waves, it gets compressed, ignites new stars, and then flows out again, leaving behind a trail of hot blue young stars that illuminate the spiral pattern. This ongoing star formation, fueled by the gas in the disk, is why spiral galaxies typically appear blue, indicating young hot stars. For a spiral galaxy to maintain its delicate disk structure, it generally needs a relatively quiet life, free from major, disruptive mergers. While minor mergers and accretion of small gas clouds can contribute to its growth, a head-on collision with another large galaxy would likely destroy its fragile disk, scattering its stars and gas. Therefore, spiral galaxies are most commonly found in less dense environments, like the outskirts of galaxy clusters, or in the vast cosmic field, where major collisions are less frequent. They are the product of relatively calm, steady accretion of gas, leading to a gracefully spinning, star-forming structure. In stark contrast to the elegant spirals are the elliptical galaxies. These are cosmic behemoths, typically smooth, featureless, and spheroidal or elliptical in shape. Ranging from nearly perfectly round to highly elongated, they lack the prominent disks, spiral arms, and ongoing star formation of their spiral counterparts. Elliptical galaxies are the cosmic graveyards, often appearing red and dead, dominated by old reddish stars, and containing very little gas or dust. Their formation history is profoundly different and typically far more violent. The primary mechanism for the formation of large elliptical galaxies is the major merger of two or more similarly sized, gas-rich galaxies, often two spirals. When two galaxies collide in such a significant way, their colossal gravitational forces tear apart their delicate structures. As we discussed, stars generally don't collide, but their orbital paths are thrown into disarray. Imagine the highly ordered, pancake-flat orbits of stars in a spiral disk being completely randomized and stirred up in 3 dimensions. This process destroys any pre-existing disk structures and creates a more spherical, dynamically hot, meaning the stars have high random motions. Crucially, the intense gravitational interactions and gas collisions during a major merger also trigger spectacular bursts of star formation. This starburst phase rapidly consumes most of the available gas, turning it into new stars in a relatively short period. Any remaining gas that isn't converted into stars is often violently expelled from the galaxy by powerful stellar winds from the newly formed massive stars and by subsequent supernova explosions. This expulsion of gas, combined with its rapid consumption, effectively quenches or shuts down star formation in the newly formed elliptical galaxy. Without a steady supply of cool gas, new stars cannot form. This explains why elliptical galaxies are predominantly populated by older, redder stars. They formed all their stars quickly during the merger, and then star formation ceased. They are the end product of a dramatic, often single, transformative event that consumed their fuel. Elliptical galaxies are far more common in the dense centers of galaxy clusters, where the probability of major mergers is much higher due to the sheer proximity and gravitational influence of numerous neighboring galaxies. These massive ellipticals at the hearts of clusters are often thought to be the result of a long history of repeated mergers and cannibalism, slowly accreting smaller galaxies over billions of years. Now let's introduce another central character in the saga of galaxy evolution, the supermassive black hole, SMBH. It is now widely accepted that nearly every large galaxy in the universe, both spirals and ellipticals, harbors a supermassive black hole at its very heart. These cosmic behemoths can range in mass from hundreds of thousands to tens of billions of times the mass of our Sun. While their direct observation is challenging, as black holes by definition don't emit light, their gravitational influence on surrounding stars and gas provides compelling evidence of their existence. How did these colossal objects come to be? The exact mechanisms are still a subject of active research, but 2 main theories prevail. One posits that they grew from seed black holes formed from the direct collapse of massive gas clouds in the early universe, skipping the stellar phase entirely. Another suggests they grew from the remnants of the very first massive population 3 stars, whose dying embers could have left behind black holes a few dozen times the mass of the Sun. Regardless of their initial size, these seed black holes then grew by relentlessly accreting gas and dust from their surroundings, and also by merging with other black holes during galactic collisions. Every time 2 galaxies merge, their central supermassive black holes are also destined to eventually merge, spiraling inwards in a titanic gravitational dance. The most fascinating aspect of supermassive black holes in galaxy formation is their coevolution with their host galaxies. It's not just that galaxies have black holes. There's a strong correlation between the mass of the supermassive black hole and the properties of the galaxy's central bulge, the spheroidal component of a spiral, or the entirety of an elliptical. This suggests a deep, symbiotic relationship, where the growth of one influences the growth of the other. When a supermassive black hole actively accretes matter, meaning it's drawing in vast amounts of gas and dust from its immediate surroundings, it becomes incredibly luminous, forming what is known as an active galactic nucleus, AGN. The infalling gas forms a swirling accretion disk around the black hole, heating up to millions of degrees through friction and emitting prodigious amounts of radiation across the electromagnetic spectrum, from X-rays to radio waves. Some AGN also launch powerful collimated jets of high-energy particles that can extend for millions of light-years into intergalactic space. In the early universe, these exceptionally bright AGN were often observed as quasars, so luminous they could outshine their entire host galaxies. The energy released by these AGN, whether through radiation or powerful jets and winds, is thought to provide a crucial feedback mechanism that profoundly influences galaxy evolution. This feedback can be both positive and negative, but its negative or quenching role is particularly significant for understanding the differences between spirals and ellipticals. Imagine a giant cosmic furnace at the center of a galaxy. As the supermassive black hole feeds, It pumps out immense amounts of energy. This energy can heat and expel gas. The powerful radiation and winds from the AGN can heat the surrounding gas to such high temperatures that it can no longer cool and condense to form stars. It also exerts a strong outward pressure, effectively pushing gas out of the galaxy's gravitational grasp entirely. This is a critical process for quenching star formation in massive galaxies, transforming them from star-forming blue spirals into red and dead ellipticals. It clears out the fuel necessary for new stars, regulates star formation. The AGN acts like a thermostat, preventing galaxies from forming too many stars too quickly. If star formation becomes too efficient, it might lead to more gas falling into the black hole, triggering an AGN outburst that then heats and expels gas, thereby slowing down star formation. Reshaped galaxies. The powerful jets from some AGN can create vast bubbles or cavities in the hot gas that surrounds galaxies in galaxy clusters, redistributing matter and energy on grand scales. This feedback mechanism is thought to be essential for explaining why the most massive galaxies in the universe are almost exclusively ellipticals, devoid of significant star formation. They likely experienced a burst of star formation during a major merger, which fueled their central black hole. The resulting powerful AGN then blew out or heated the remaining gas, effectively shutting down further star formation and leaving behind a red and dead elliptical. Spiral galaxies, on the other hand, are thought to have either avoided such major gas-consuming mergers, or their AGN were less active or more gentle in their feedback, allowing them to retain their gas and continue forming stars. Beyond internal processes and black hole feedback, the environment in which a galaxy resides also plays a critical role in its evolution. Galaxies in dense environments, such as the hearts of massive galaxy clusters, experience different evolutionary pressures than those in isolation. Ram pressure stripping. As a galaxy moves through the hot, diffuse gas that permeates galaxy clusters, it experiences a strong wind that can literally strip away its own cool star-forming gas, much like the wind stripping leaves from a tree. This ram pressure stripping can quickly quench star formation in spiral galaxies falling into clusters, transforming them into red, gas-poor systems, often with distorted, jellyfish-like tails of stripped gas. Tidal stripping. The strong gravitational fields of neighboring galaxies within a dense cluster can exert powerful tidal forces on a galaxy, pulling away its outer stars and even entire dwarf galaxies. This can contribute to the growth of central cluster galaxies and deplete the stellar halos of smaller galaxies. Harassment. Frequent, fast encounters between galaxies in dense clusters can also subtly disrupt galaxies over time, gradually stripping away gas and disturbing their structure. These environmental effects, combined with merger histories and black hole feedback, paint a complex picture of galactic evolution. It's not a single pathway, but a tangled web of influences that ultimately determines a galaxy's final form and stellar content. Our own galaxy, the Milky Way, is a classic example of a spiral galaxy that has largely avoided a major disruptive merger in its recent history. It continues to accrete fresh gas from the cosmic web, fueling ongoing star formation in its disk, and its central supermassive black hole, Sagittarius A-Chon, is currently relatively quiescent. However, our galaxy's story of evolution is far from over. In about 4.5 billion years, the Milky Way is on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy, which is also a spiral. This will be a truly spectacular major merger event, transforming both galaxies over hundreds of millions of years. Their disks will be destroyed, their stars flung into new orbits, their central black holes will likely spiral into each other, and the resulting combined galaxy is predicted to be a giant elliptical, which we might colloquially call Milkomeda. Thus, the journey from galactic toddlers to grand designs is one of immense cosmic forces at play. The patient pull of gravity, the transformative power of mergers, the life-giving and life-quenching influence of supermassive black holes, and the shaping hand of the environment. Galaxies are not static entities. They are dynamic, evolving systems, constantly growing, transforming, and interacting over cosmic timescales. We have witnessed the universe develop from a featureless expanse into a tapestry woven with magnificent spirals and majestic ellipticals. But even these grand designs are not the final chapter. The universe continues to expand, and galaxies continue their slow, inexorable dance, moving towards a future that is still being written in the vast cosmic expanse. The next and final chapter will reflect on this ongoing evolution and the questions that still beckon us into the cosmic unknown. Chapter 6: Our Galactic Home and Beyond. The Future of Galaxies. We have journeyed together through cosmic time, from the nearly featureless, superheated aftermath of the Big Bang, through the patient weaving of the invisible cosmic web by dark matter, and into the profound moment when the first stars ignited, banishing the dark ages and chemically enriching the universe. We then witnessed the chaotic yet fundamental era of galactic toddlers, where proto-galaxies grew through ceaseless mergers and gas accretion, gradually giving rise to the magnificent, distinct, grand designs of spirals and ellipticals, their evolution inextricably linked to the enigmatic supermassive black holes lurking at their cores. Now in our final chapter, we bring this grand narrative home to our own cosmic neighborhood, reflect on the ongoing evolution of galaxies, peer into their distant future, and humbly acknowledge the vast frontiers of discovery that still await us. Our own galactic home, the Milky Way, a majestic barred spiral galaxy, stands as a testament to the principles of galaxy formation we've explored. It is not an anomaly, but a typical product of the cosmic processes that have unfolded over the past 13.8 billion years. Our galaxy resides within a larger dark matter halo, part of a filamentary structure in the cosmic web that astronomers have now mapped out as the Laniakea supercluster, a vast collection of tens of thousands of galaxies, all gravitationally bound, including our own local group. The Milky Way's history, like that of any large galaxy, is one of hierarchical growth. Its initial dark matter halo formed early on, accumulating primordial gas, which eventually cooled and condensed to form the first generations of stars within it. But our galaxy didn't just grow from the inside out. It grew by continuously accreting smaller structures. Evidence for this lies scattered throughout our galactic halo. Billions of ancient metal-poor stars that don't follow the ordered rotation of our disk, but instead form a diffuse spheroidal component. Many of these stars are thought to be the stripped remnants of smaller dwarf galaxies that the Milky Way has cannibalized over billions of years. We can even see fossil evidence of this ongoing galactic consumption in the form of stellar streams, long, thin rivers of stars pulled out of disrupted dwarf galaxies as they are torn apart by the Milky Way's immense gravity. The Sagittarius dwarf spheroidal galaxy, for instance, is currently being slowly devoured by our galaxy, its stars gradually incorporated into our halo. The globular clusters, tightly bound collections of hundreds of thousands of very old stars that orbit our galaxy's halo, are another relic of this early, turbulent past. These are thought to be among the oldest stellar populations in the Milky Way, perhaps representing the cause of some of those earliest proto-galaxies that eventually merged to form our larger system. Our galaxy's central bulge, a dense, roughly spherical concentration of older stars, also bears the hallmarks of a rich merger history in its formation, possibly a product of numerous early collisions that randomized stellar orbits in the galactic core. And at the very heart of the Milky Way, nestled amidst a dense swarm of stars, lies our own supermassive black hole, Sagittarius A.T. Faint gravitationally flaring as small gas clouds or stars get too close. Its immense gravitational power, over 4 million times the mass of our Sun, is undeniable. Its presence confirms the ubiquitous link between massive galaxies and their central black holes, suggesting that our galaxy too experienced phases in its youth when its black hole was actively accreting, perhaps even as a quasar, before settling into its current, calmer existence. The Milky Way's majestic spiral arms are a testament to the continued inflow of cool gas from the cosmic web, allowing for ongoing star formation in its disk. Our Sun, a relatively metal-rich star, formed from this gas about 4.6 billion years ago, a testament to the chemical enrichment that occurred over cosmic time, making possible the planetary systems that harbor complex life. We live in a mature, active galaxy, still forming stars, still subtly growing. But the story of galaxy evolution is far from over for the Milky Way. Indeed, it's just beginning a new, dramatic chapter. Our galaxy is on a direct collision course with its nearest large galactic neighbor, the Andromeda Galaxy, another massive spiral, about 2.5 million light-years away. For billions of years, these two colossal systems have been drawing closer due to their mutual gravitational attraction, overcoming the universe's expansion on this scale. In approximately 4.5 billion years, our two galaxies will begin a spectacular slow-motion cosmic dance, a major merger event that will fundamentally reshape both systems. This will not be a head-on smash of stars. Instead, the two galaxies will gravitationally pull and stretch each other, passing through one another multiple times over hundreds of millions of years. Their immense gas clouds will collide, triggering furious bursts of star formation. The ordered disks of both spirals will be destroyed, their stars flung into new, more randomized orbits. Eventually, the two central supermassive black holes will spiral inwards towards each other, emitting powerful gravitational waves before merging into a single, even more massive supermassive black hole. The final product of this titanic collision is predicted to be a giant elliptical galaxy, which astronomers playfully dub Milky Way. This future event, distant as it may be, is a powerful reminder that galaxy formation is an ongoing, dynamic process, not a static snapshot in time. The universe's journey is an unfinished symphony, and the evolution of galaxies continues throughout cosmic time, though the pace and nature of that evolution have changed dramatically. In the early universe, as we've seen, galaxy formation was frenetic. The universe was denser, gas was more abundant, and mergers were far more frequent. This led to a higher rate of star formation across the cosmos. Scientists have observed that the peak era of star formation occurred roughly 8 to 10 billion years ago, when the universe was only a few billion years old. Galaxies were forming stars at a much faster rate than they are today, appearing bluer and more irregular, reflecting their violent, active youth. Today, the overall rate of star formation in the universe has significantly declined. Why this cosmic slowdown? Several factors contribute. First, galaxies are simply running out of the raw material, cool gas. This gas has either been consumed by star formation, locked away in long-lived stars, or violently expelled from galaxies by powerful supernova explosions and active galactic nuclei feedback, becoming too hot and diffuse to form new stars. Second, as the universe has expanded, the cosmic web has stretched, and structures have become more isolated. The supply of fresh gas flowing into galaxies from the filaments has dwindled. Third, the continuing mergers of gas-rich spirals into gas-poor ellipticals, as discussed, effectively quenches star formation in these massive systems, creating red and dead galaxies that produce no new stars. This phenomenon is sometimes referred to as cosmic downsizing, where the most massive galaxies formed their stars earliest and are now mostly quiescent, while smaller galaxies continue to form stars at a slower pace. The universe is undergoing a kind of desertification in terms of star-forming regions. Looking much further into the cosmic future, the fate of galaxies is intrinsically linked to the ultimate fate of the universe itself. We now know that our universe's expansion is not only continuing, but also accelerating, driven by the mysterious force of dark energy. This accelerating expansion has profound implications. Over unimaginably vast timescales, distant galaxies will recede from us at speeds greater than the speed of light, eventually passing beyond our observable horizon. We will no longer be able to see them, their light never reaching us. Our local cluster of galaxies, the local group, and perhaps even the larger Laniakea supercluster, will remain gravitationally bound, forming an isolated island of galaxies in an ever-expanding, increasingly empty void. The vast cosmic web, stretched beyond recognition, will dissolve for any future observers. Within these isolated galactic islands, stars will continue their life cycles until all the available gas is exhausted. New star formation will eventually cease entirely. Existing stars will age, swell into red giants, and then gently fade into white dwarfs, or explosively end their lives as supernovae, leaving behind neutron stars or black holes. Over trillions upon trillions of years, the universe will become a cold, dark place, dominated by these stellar remnants. White dwarfs will eventually cool into black dwarfs, neutron stars will remain, and stellar mass black holes will populate the cosmos. Even black holes, those cosmic vacuum cleaners, are not eternal. According to the theoretical work of Stephen Hawking, black holes slowly evaporate over truly mind-boggling timescales by emitting Hawking radiation. The most massive black holes, including the supermassive ones at galactic centers, would take googles of years, a 1 followed by 100 zeros, to completely evaporate. After this unfathomable amount of time, the universe would be left with a diffuse soup of fundamental particles, protons decaying into even more fundamental particles, and an almost complete absence of structure, heat, or light. This is the bleak but scientifically plausible scenario of the big freeze or heat death of the universe. While we have pieced together this intricate story of galaxy birth and evolution, it is crucial to acknowledge the vast realms of the unknown that still beckon us. The universe, in its boundless complexity, continues to hold profound mysteries. What exactly are dark matter and dark energy? These two components, which collectively make up 95% of the universe's mass energy content, remain the biggest enigmas in modern cosmology. Understanding their true nature is arguably the most significant challenge facing physics today, and it will undoubtedly reshape our understanding of how galaxies form and evolve. We still have much to learn about the very first stars and galaxies. Can we ever directly observe a population 3 star, or the elusive dark galaxies thought to be made almost entirely of dark matter? How did the first supermassive black holes form so early in the universe's history, seemingly growing disproportionately fast compared to their host galaxies? The intricate dance of feedback mechanisms, how energy from supernovae and active black holes truly impacts the surrounding gas and regulates star formation, is still being refined in our models. How do mergers versus smooth gas accretion dominate in different types of galaxies and environments? These are not trivial questions. They represent the cutting edge of astrophysical research. Our understanding of this cosmic narrative comes from a remarkable combination of ingenuity and persistence. Observational astronomy is our primary window into the universe. Powerful telescopes across the electromagnetic spectrum, from radio waves like the Atacama Large Millimeter Submillimeter Array, ALMA, studying cold gas in distant galaxies, to visible light like the Hubble Space Telescope, giving us stunning views of galaxy mergers, to X-rays like the Chandra X-ray Observatory, detecting hot gas and black hole activity, allow us to peer back in time because light travels at a finite speed. Looking at distant galaxies is literally looking at the universe as it was billions of years ago. The James Webb Space Telescope, JWST, is revolutionizing our view of the early universe, allowing us to see some of the very first galaxies forming, acting as a cosmic time machine. Large-scale surveys, meticulously mapping the positions of millions of galaxies, reveal the intricate structure of the cosmic web, confirming the predictions of dark matter. Complementing observations are cosmological simulations. These are immense computer programs that, starting from the initial conditions observed in the cosmic microwave background and applying the known laws of physics, gravity, gas dynamics, dark matter behavior, model the evolution of the universe over billions of years. These simulations, running on supercomputers, allow scientists to test different theories of galaxy formation, watch how dark matter halos grow, how gas falls in, how stars form, how black holes evolve, and how galaxies merge and interact. While they are complex, they provide crucial insights into processes that are too vast, too long-lived, or too violent to observe directly in real time. And underpinning all of this is theoretical physics, constantly developing new models and frameworks to explain the mysteries that observations and simulations present. It's a dynamic interplay. Theories predict, observations confirm or challenge, and simulations provide a bridge between the two. As we conclude our exploration of how galaxies are born, let us take a moment to reflect on the sheer immensity of this cosmic story. From a universe that began as an almost perfectly uniform soup of particles, to the intricate dance of invisible dark matter and the slow, inexorable pull of gravity, leading to the birth of the first fleeting stars, and then the assembly of colossal island universes. The process is one of profound beauty and staggering complexity. It is a story of transformation, of matter constantly rearranging itself, from the simplest hydrogen atoms to the magnificent spirals and ellipticals, within which new generations of stars forge the very elements that make up planets, water, and ultimately, us. The universe is a cosmic nursery, always creating, always evolving. We, as fleeting inhabitants of one small planet, orbiting one average star in one spiral arm of one galaxy, are products of this grand cosmic ballet. Our existence is intimately tied to the processes we have discussed. The Big Bang created the hydrogen and helium. The first stars and their descendants forged the carbon, oxygen, and iron, and galaxies provided the sheltered environments for these elements to come together to form planets and eventually life. The journey to understand how galaxies are born is not just about understanding distant objects, it's about understanding our own cosmic heritage, our origins, and our place in the vast unfolding story of the universe. The scientific quest continues, and the universe, in its boundless wonder, will surely reveal many more secrets to those curious enough to ask the questions and patient enough to seek the answers. Thank you for joining me on this incredible voyage.